All right, let's get started with our lecture today. So the plan for today is we'll go over 2 chapters because I'm trying to kind of cut off the material from today, like up to today's lecture for our exam 1. So I want to give you kind of a buffer of 1 extra week to prepare for the exam, so you know all the material beforehand. So that you can start preparing early. And chapter 5 and chapter 6 is kind of short. Well, chapter 2 for now is the longest one. Well, now, yeah, hopefully it won't take too long for today. Let's just get started. So for chapter 3 and chapter 4, we covered random variables. Either continuous or discrete, have some basic concept for those random variables. And for today, like chapter 5, we'll talk about sampling statistics. This is when we kind of blending our new probability knowledge with data and statistics. So sampling statistics, sampling distribution, it's something about a sample. So when you collect the data. So we compute statistics from our sample. This is a term. What is statistics? So it's just any quantity where those value can be computed from our sample data. So statistics is kind of in parallel with parameter. Parameter is you're characterizing something about a population. And now statistics is something that you trying to capture from the data. So we have some like typical statistics that we deal with a lot. For example, we do sample mean and sample variance or sample standard deviation a lot. So let's just define it anyway. What is the sample mean? Where it's just the average of a sample. Or if we see the sample is x1 to xn, we normally call the sample mean as x bar. So just sum them up divided by the total sample size as our sample mean. And for sample variance, we use S square instead of sigma square when we do sample variance, right? And it's the formula is like this. It uses n-1 because it's kind of related to a degree of freedom. But anyway, this is just the formula to calculate the standard, the sample variance. And the standard deviation is just the square root of the sample variance. And it's better that that we just import our data in R and you just do the mean function and like the SD function to get the standard deviation for your sample data. So that's how we calculated. Yeah, so if you still remember this sample mean, like mean and standard deviation, they are trying to measuring the center and the spread for our data. So in general, we use them to make estimates about the center and spread for the population where the sample was taken from. So we use this statistics, just trying to get a feeling, get some estimate get a feeling about the population. Okay. Well, because there is uncertainty about the value of the data that we collected. So before we do the computation, the data by itself has some uncertainty, the sample. So there would be a probability attached to it. So a statistics is a random variable. So that's how. So we learned probability like those densities, or like when we're talking about random variables, we're talking about PDF, CDF. So statistics is still a random variable where we can get some like probability characteristics about this random variable. So normally we use the uppercase letter to denote random variable statistic and a lowercase letter to represent the observed. So for example, the sample mean, we use this X bar, capital X, upper letter. And once we got our sample and calculated the observed value, that's denoted by small x bar. Similarly, for the sample standard deviation, we use this S for this sample standard deviation random variable. And once we got our data, we calculate the sample standard deviation. We use this small s to denote the sample standard deviation we calculated with the data. So yeah, this is the connection of the statistics with probability because it's a random variable. So why we care about this, about the population parameters? Like for example, why we care about those like statistics? Because we care about population parameters. That's the way we use to get an estimate for the parameter for the population. For example, this is just example for population parameters. Like what's the average height of the population and what's the average height of group 1 different than the average height of group 2. So that's where we would have to use statistics to make inference about this question, trying to answer this question. Yeah, population is generally really large. We cannot sample like every like elements in the population. So we would only have samples. So we can only work with sample statistics. And by knowing the distribution of these random variables, I mean, the random variables is the statistics now we are talking about. It allows us to do, I should say, to do inference, to do, yeah, this statistics is more generally statistics. So if we have average height from samples of groups about like group 1 and group 2, and we can make inference on how far apart, it's far apart enough to say the groups have different population mean. Like in statistics, we call it like significantly different from each other. That we'll talk about that in later chapters. So here is just a note about random samples. So when I say a sample, I typically mean it's a random sample. And normally people will see it's an IID sample, where it means the sample, the random variables that you collected are independent and they have the same probability distribution. That's what identically distributed. So they have the same probability distribution. Yeah, that means they are all taken from the same population. Yeah, that's called IID sample, and yeah, just kind of about the notation for samples. So now, why is the normal distribution so important? Well, there are lots of reasons about why we talk about normal distribution so much, and the most important one is that if you do a linear function of a normal random variable, for example, if x is normal, then you do a linear function of this x. So this y is also normal. So this is how we made the standardized normal z last week. Now we're going to use this conclusion to find the sampling distribution of x bar. So this is our sample statistics, sample mean. We want to get the distribution of our sample mean. Previously, we were talking about the distribution of x, a random variable x. Now we get its sample mean, x bar. and now we want to get its sampling distribution. So what is a sampling distribution? It's the probability distribution, just like what we learned from last 2 chapters of a statistic. Now it's about statistic. It's of an infinite number of random samples from a population. Well, we cannot draw really an infinite number of samples. So this is kind of theoretical quantity, but we will use this theory to make inference about our sample and the population. So generally, it's better to get a large sample size, trying to be more precise when we're trying to characterize your population. So when we do this sampling distribution, it says an infinite number of random samples. Generally, it's like a large number of random samples. Okay, why we need this sampling distribution? Let me just put everything here. In short, because we want to do inference about the population, and when we're trying to do sampling distribution, when we're trying to get the information about a distribution, that's because when we want to do some inference, we will need the distribution to like do our calculation. For example, here, if we know, for example, we have data x1 to xn from a normally distributed population. We know their standard deviation, but not the mean. How do we estimate the mean? We know we just take a sample, get the sample mean for the estimation of this population mean, right? But this is just the point estimate, and we would prefer to get an interval estimate, so that gives us kind of a error bound for your estimation. We know how much uncertainty we have for a particular estimate. Where when we have only one single point estimate, we only know that that's just one data point that we estimate. But if we have an interval estimate, we can quantitate the uncertainty. But when we were trying to quantify the uncertainty, that's kind of all for what statistics is doing. Well, when we were trying to get the interval, we would definitely need this distribution. You will see this, I think when we do, chapter 7, it's about interval estimation. So in order to get this interval estimate, we would need the distribution of x bar. So that's our sampling distribution. This is why we need to learn this sampling distribution. Okay, sample distribution for the mean of normal data. So now we only focus on the normally distributed data and look at what the sample distribution of x bar. So now we see x1 to xn, they are IID, and from normal with mean mu and variance sigma square. So this is a variance. We are trying to get the distribution of this sample mean. There is this x bar. I would see this x bar is normal. Why? Because we said if we do a linear transformation of this x, it's still a normal distributed random variable. Let's do the calculation. I'd like to put everything here. So we need the mean to get the expectation. Where is the expectation? Well, this is just the formula. Yeah, this is just the formula. How do we get the now we know the X bar is normally distributed because linear transformation of this X is still a normal random variable. And now we need to get its mean and its variance. Right, that's the two parameters for normal distribution. So the calculation for the mean is just you take the expectation of this X bar and just plug in, and this X, like 1/n would come odd, and this summation of this Xi, so each of them have mean being mu, so you have n of them to sum together, so it's n times mu divided by this n. So this mu X bar is just mu, where this mu is the mean of X.
So the little X, or is the mean the big X or the little X?
So when I have this mu here, it's for this big X. So you see here x1 to xn, there are ID following normal with mean mu, right? And when I talk about this mu X bar, this is the mean for X bar, where this X bar is just like calculated as this.
So can you use the n times mu over n to find the mean? That'll still give you the mean.
You mean the mean of X bar?
Yeah.
Yeah, actually, I'm just showing you how do we get this mu X bar is just equal to mu. So you can just directly use this. This is kind of a conclusion here, where the mu of X bar is just the mean of your data.
Yeah.
Yeah. The mean of your sample mean is the same as the mean of your data. So the data is x1 to xn, and the mean of the population, I should say. So they are equal. So just make sure you know now we are talking about this X bar. We want to get its distribution. That's what we call sample distribution because it's the sample mean. So we know X bar is normally distributed, and we just need to find the mean of this X bar and the variance, the sample variance for this X bar. So if this is kind of confusing, you can just ignore this calculation. You need to know that mu X bar just equal to mu. And the sigma square X bar is just the sigma square, but divided by n. Yeah, if you're curious why, now you can look at the calculation. That's why I put the calculation here. So now, yeah, kind of. So now we know this X bar following normal distribution, and now we know the mean of X bar is actually just mu. And the standard, this is the variance. The variance of this X bar is just sigma squared divided by n. But depending on the notation, sometimes we can also write this X bar following normal with mean mu and the standard deviation being this. So I think just for, it's easier to remember, like, because when you do R coding, it's just asking for the mean and the standard deviation, not the variance. So we will use this like standard deviation notation for this normal distribution. Yeah, so this is something important. Yeah, we have an example here. Suppose we know that for a population, the weight is normally distributed with mean mu equal to 53 grams and standard deviation sigma equals 0.3. So this is the parameters for the population that we are assuming that we know them. Now we consider a random sample of 4 subjects from this population. So now we get a sample of size 4. So we get our data, and we can get the sample mean, where the sample have only 4 data points. We get the sample mean, and we know this sample mean is also normally distributed. And we also know the sample mean, the mean of the sample mean, I should say, the mean of the sample mean is this, just the population mean, where it's 53. And the standard deviation of this sample mean is the sigma divided by square root of n, where the sigma is the population standard deviation. I know it's kind of confusing, but just make sure you know, now we talk about the sample mean, x bar, and we're trying to figure out what is distribution. And how to calculate it once we know this, once we know the information about the population. So yeah, since we know the distribution of the sample mean, now it's normal with mean 53 and a standard deviation 0.15. Now we can calculate all different probability stuff, such as what is the probability of this x bar less than this quantity for a sample size of 4. So we know the distribution of x bar already, and we can just do what we did from last chapter. So this is what you do in R. You just use this P norm, where I think it's for the CDF. Yeah, it's CDF less than something. It's for the CDF, and you put the mean and the standard deviation here to get this probability. Now, if we do the calculation, the probability is small. It's 0.0004. And alternative way to get this is to kind of standardize this x bar to this z, where you do the same operation on the right hand side, where you can get this equivalently for this. This probability is small. What does that mean? Probability being small, that means it's very unlikely that your sample will have an average of that small, like less than 52.5. So if you do get a sample like this, it's either because something is up with your sample, like when you do the sampling, either it's not random or it's biased, or the mean, where we were supposing that we know. How did we get the 52.5? Okay, so this is kind of given to you. This is asking you what is the probability of x bar less than this 52.5. So it's kind of the question statement is asking you about to calculate this quantity. So this will be given. It's not calculated or whatsoever. And when we really learn about hypothesis testing, you will know, well, what this means. Oh, yeah, it's given for now. And when we talk about hypothesis testing, it's kind of a different story. But for now, it's just given and trying to ask you what's the probability. And I'm just showing you how to get the probability. And about this, so this statement is trying to link this to what we are going to learn in the future. So when we see something like the probability is small, that means it's very unlikely that you see something that you see the average being like less than 52.5. And it means there's something wrong. And when we do the hypothesis testing, that's what we will see. Yeah, we will talk about that in, yeah, I think it's in chapter 8, chapter 8 or 9. Okay, another example here. Well, yeah, let me see if I have this in the R. Okay, yeah, this is for the second. This is the second example. Oh, okay, yeah. So okay, let's just look at the slides first before we go into R. So suppose that the distance a golf ball flies is normally distributed. So this distance, this random variable, that is are random variables in sample distribution always positive? No random variables in sample distribution. Okay, this is so random variables, they can take any value actually, like depending on what distribution they are following. For example, now we are talking about normally distributed random variables. It can certainly go negative. For example, when we have a mean 0 for the normal distributed variable, on the left of its mean, it would be negative, right? We have symmetric shape for normal distribution. So theoretically, we would have half of them being negative if we have a standard normal distribution. So no, it's not always positive. It can take negative values. Or for some distribution, like when we talk about random variables, like exponential distributed random variables, they would always be called positive. But for example, uniform distributed random variables, they can certainly go negative. Normal distributed variables, they can go negative, and the list goes on and on, because there are so many distributions in statistics.
Can you go back where you they calculated 315?
Yes. Yes.
I think it was the other slide.
Okay, the previous one here. Yes. Okay. Now we go to this example, and now we know this distance is normal distributed. So this distance a golf ball can fly is normal distributed, and we know the mean is 435 and the standard deviation 36. So this is giving you mu equal to 435 and sigma equal to 36, which is for the population. For the population, for basically for X, the distribution of X. Oh, I hope I can write here, but so this statement is telling you X following normal distribution with mu equal to 435 and sigma equal to 36. So if X bar is the sample mean of this random variable X, I call this distance being X, and of this many shots, so this is our sample size, so this is N. Now it's asking what's the distribution of X bar. This is a very typical question for the sample distribution, where we know mu is 435, and we know mu X bar is just equal to mu. So I put this 435 mu here. And we also know mu X bar, sigma X bar. So the standard deviation for X bar is just the sigma over the square root of N. So that is 36 over square root of N. Where is the square root of this 36? That's 6. So the just the final solution for this sample standard deviation is just 6. So how I get this 6 is 36 over the square root of 36. So now it's asking what's the probability that 36 shots travel an average of less than this many feet or more than this many feet. Well, now it sounds familiar, right? Once we get the distribution of this x bar, now this one is just asking what is the probability of x bar less than 430, and what is the probability of x bar greater than 450. And what does this look like on the graph of the PDF? I believe I have this.
You put P norm parentheses 430, 435, 6, right?
P norm. Yeah, that's for the CDF. When it's asking for this less than, right?
Right.
Yeah, less than is for the P norm is for the CDF. I think I have the code here. And when you do this more than something, you have to do 1 minus the probability of less than. Okay. Oh, well, this is not the. Well, I think I didn't put the code for this example here, but it's for. Oh, this is strange. I thought I put it here. Yeah, I think I only did that lab for this last example. Well, anyway, we will see that how we code it up in R in just a bit. So before we go to R, let's talk about this. One very important thing is called central limit theorem. It's very useful and very important theory to for us to draw conclusions about statistics. So now everything we talked about previously, depending on that we have the variable x following normal, and then we can talk about the distribution of x bar. But yeah, I just reiterate that because we were taking the linear combination of that normal random variables in order to make the inference to get the distribution. Where this central limit theorem is a bigger and more powerful fact that this is what it is. If x1 to xn are IID with mean mu x, so this is the mean of this x and variance sigma square x, then, well, note that we didn't say anything about particular distribution. We didn't mention that it's normal distributed, so we didn't make any assumption here about the distribution. Then as the sample size n gets larger, the distribution of x bar would convergence to this normal distribution. So it's still it will be normally distributed with mean mu x and standard deviation sigma x divided by square root of n. So this formula is the same. Now the only difference here is that we didn't say that x is following normal distribution here. But the condition here is that the sample size needs to be large so that we can have this results.
So you said x is not a linear?
So previously, like when we haven't talked about this central limit theorem, we were assuming x is following normal distribution. Yeah, so that x bar have this very similar distribution. And now we no longer assume that. We're just saying x all this X or ID have this mean, have this variance. If we have a really large sample size, we can still get this normal distribution. So the question here is that how large does our sample needs to be in order to like get eventually to this distribution? Well, this sample size would depend on whether you know or you do not know this population standard deviation, sigma x. I put a rule of thumb here. So if you know, this is from the book. If you know this standard deviation of your population, this about x, the sample size n greater than 30 would be sufficient. But if you do not know this sigma x, we would need n being greater than 40 in order to get this conclusion, in order to say that x bar is following this distribution. Yeah, and in this case, because we do not know the sigma x, we would have to use the sample standard deviation for this one to replace this one. Yeah. Well, when you deal with real data, this is not like very strict, but this is kind of just a rule of thumb. When data collection is hard, people would still use this conclusion, like this normal distribution for the sample mean, even though the sample size is not strictly greater than 30. So it's kind of depends. Yeah, this 30 and 40 is just a rule of thumb. Example, yeah, now we can go deeper on this example. They are very much similar, like all three examples are very much similar. Suppose the time it takes you to get to and from work has a normal distribution. So now we assumed that x is normal distribution with a mean of 45 minutes and standard deviation of 7 minutes. So x is following this. It's a good practice that you always write this down when you read the statement here. Now it's asking what's the distribution of this x bar for, that is the average trip time for 5 weekdays worth of commuting. So x bar is the average trip time for 5 weekdays of commuting. Just use our formula. Once we know this, we can write the distribution of x bar as this, because their mu are the same and their standard deviation are different by this. We have to divide it by the square root of n. And we know n equal to 5 in this case. So what is the probability? Yeah, once we know the distribution, now we can calculate the probability. What's the probability that your average time was less than 40 minutes? Your average time, that's asking about is x bar. So this is probability of x bar less than 40. And we have kind of a bunch of different questions. This one is just greater than 46 and less than 50. And now this one is a bit different. It's asking about the probability that tomorrow's trip will be longer than 50 minutes. So it's no longer asking about the average. It's asking about x instead of x bar here. So when it refers to average, you know it's asking about the sample mean, it's the x bar. But here it didn't say anything about the average. It means it's asking for your data X. So this is asking for the probability of X greater than 50. There was the 90th percentile of the average. So again, this is asking about the average. And I can also ask for like the percentile of X by itself. So this is something to pay attention when you read the question. Yeah, let's go to the R. The first one is probability of the average time less than 40 minutes. And again, we just use this when it's less than, we do this P norm, and we specify the mean and the standard deviation of this X bar. We're doing things about this X bar. The second one is a difference of two area on the CDF. If you still remember what it means when we were asking about the probability of a range, it's you take the probability, the area of a bigger value minus the probability of the smaller, the area of a smaller range on the left. Well, I remember I did yeah, I do have a plot to show you, but anyway, this is how you do the calculation for a range. So when it's asking about the probability of tomorrow's trip more than 50 minutes, it's asking about X. And again, remember, it's asking like more than 50 is greater than. When you say greater than, you have to do the 1 minus in order to do this P norm thing. And specify the right mean and standard deviation for X. And
so because that one's only asking for 1 day's worth of
yeah, it's not, yeah.
You're not going to put the square root of 5. You're just putting the standard.
Your X. You know the distribution of X. That's your data. That's the population you sampled the data from. Where X bar, you know, is the average.
Yeah.
And if it's asking for like tomorrow's trip, it's just this. Yeah, for the X, it's not the average. Week average more than 50. So this one is about average. You do the probability of X bar greater than 50. So whenever you do this X bar, make sure you put the information for X bar, not the information for X. This one, because we are talking about this X, you put the mean and the standard deviation of the X there. Yeah, there are several steps. You have to be able to tell what is asking, whether it's asking for the probability about X or it's asking the probability of X bar. And then you can start coding up. Yeah, asking for X, you put distribution for X. Asking for X bar, you put the distribution for X bar. Cannot make this wrong. And asking about the 90th percentile of weeks for weeks of trip. So yeah, that's for the average. Yeah, the average trip time. So I'm answering these questions. For the average trip time, the 90th percentile. So again, I put the distribution for X bar here. Similarly, if it's asking for 1 trip, that's about X. Yeah. So now I'm just showing you. So I get a sequence of data and get the density for the data. I'm trying to make a plot of control.
So they asked for the average of, what was the word? X, if it's the average, you're gonna use X bar.
Yeah, X bar.
If you're only looking for one number,
We'll just do the 1 minus
then that's if you're looking for something greater.
Yeah.
Yeah,
more than
yeah. If it's like less than 50, then you're doing the regular.
the P norm.
Mm. Yeah, it takes practice in order to remember all of this.
Yeah, because it's like understanding the concept and then implementing and parsing it.
Yeah. Actually, using RStudio is actually easier or quicker comparing to you look up tables. Actually, when you really work or use this information, you would never go to those tables. That's why now we learn how to do this in R. So yeah, some people feel R is hard to get, but once you get it, you find it's easy.
Give me both.
Yeah. So yeah, I'm showing you a plot of the PDF to show you like kind of the error thing. So this is for this my Y1 is for the X bar. If you this PDF of X bar, because I used this standard deviation, right? This is for X bar. And Y2 is for X. So now I plot this X bar. It's normally distributed. It would be like this. And I did a vertical line at, oops, I haven't run this. So I get the 90th percentile for the average, which is our A, and A is, A is this 49 something. And I'll put this onto here. So this is our 90th percentile, where you have this area being 0.9. The area on the left of this line being 0.9. That's the 90th percentile located at here. And yeah, so this is for X bar. I'd better just do, I'll choose that later. And the second line, which is in blue color, I'm plotting the PDF of X. So this is the PDF of X, where you see it has a wider spread because the standard deviation for X is larger than the standard deviation of X bar, right? Because it has a square root underneath for the X bar. So this is a PDF for the X bar, and I add the 90th quantile for this X bar. And on the left-hand side of this green vertical line, it's 0.9. The area on the left of this blue of this green.
Oh, the green is the 90th percentile.
Yeah,
of
this
the
is
green
also
one
the.
and black one.
Yeah, the black one is for X, and the green one is for X bar. Did I make it backward? So the the black one is for X bar. The green one is for X.
I didn't know like color wise.
Oh, so this is like when I do this point. So this previously, let me just redo this plot. where I only specified we use the line type is just the regular line. And I didn't specify the color, where it's by default being black. And if I want to add something onto this existing plot, I use these points, where you can just add like single points to this existing plot, or here I added like a sequence of points, so it connected to a line. And I specified use line type to connect those points, and also specify the color being it's the third in the color vector. The third one represents green, like the second one represents yellow, red. It's just,
You can find what color represents what number on Google, right? Like
yeah,
okay.
yeah. Like if I use this color equal to 2, it will be I think it's a red one. Yeah, yeah, it's a red one. Oh, this one if I do this 2 as well, yeah, it will just yeah, I think that's I have this plot here just trying to show you just trying to reiterate about this percentile concept. So what this means and how you find its use are. Okay. So this is for chapter 5. Now I'm going to have chapter 6 as well. Chapter 6 is short. Actually, there are like lots of information about point estimation. But I think I'm just like picked the most important things that you will probably use in the future. So we'll only cover those important ones. Okay, this is point estimate. Well, previously we talked about sample distribution. We actually will use that. Yeah, we'll use that a lot. And this point estimate, I think you will use this more often. Yeah, if you will use this point estimate like pretty often, but only the very, very shallow concepts. If you do like research, or if you do like statistical related research, like knowing about how to do this estimates is kind of important, because different method of estimation would give you different quality for your estimates, and also the characteristics of your estimates. But here we'll just cover the easy one. So, well, I think this, yeah, we'll always trying to get a conclusion about parameters for a population. And we know it's hard to get it, so we get a sample and do our estimate, use our sample. Previously, when we tried to get the mean and the variance of a sample, you're actually making estimates of the mean and variance for the whole population. So this is just one type of estimation. If we estimate X bar from a sample, we can use it to draw conclusions about the mean of the population, mu. So this X bar is our point estimate for this mu. And there are, well, this is just one example for this parameter mu. And there are so many different parameters. For example, we talked about lambda when we refer to exponential distribution. We can ask what is the point estimate for lambda, or like probability, proportion P, what is the estimate for P when we refer to a binomial distribution. Yes, and
So sorry, so X bar is the mean of the sample, and then
Yes.
is the mu,
mu,
it's the mean of the whole population.
right.
Hey, it started too quick, okay?
Okay. That's, well, yeah, I actually gave you examples already about this point estimate, but let's do it again with this general denotation theta. For parameter theta, a point estimate for this theta is a single number that will be treated as like sensible value for theta. So that's a point estimate. So when we try to do an estimate, we think, okay, this estimate should be close to the true value of the parameter. And how we get this, we get from sample data and this selected statistic, like our estimate, is often denoted by put a hat on it, like theta hat, p hat. P normally refer to proportion, p hat. And this, well, this X bar is kind of special. We normally just use the X bar as the estimate for mu. And if you have, and we use the S as the estimate for sigma. Or in general, you can use like mu hat to refer to a general estimate, or like sigma hat to refer to a general estimate. But normally we just use X bar and S for estimator of mu and sigma. Example here. Suppose that a factory is interested in what proportion of their product produced are faulty, but they cannot test every product. So they want to know the proportion of their product being faulty. So they want to know the parameter P being the proportion of products that's 40. And this P is a population parameter. And the population is the factory's product. It produced so many products that you cannot test every product. So we just draw a sample, see a sample of size N, and we denote the number of the 40 products in this sample by X. So see, we take a sample of 50 products, so N equal to 50. And test those and find 4 of them, 4 of the sample are faulty. So 4 of them, so this is saying X equal to 4, because X is the number of faulty products. Now we know the value of small x and our sample size N. We can do an estimate for this proportion P. We denote the estimate by P hat, and trying to find a proportion, that's normally we do like the total number of something divided by the, here is the total number of the faulty products divided by the total sample size. So in this case, our estimate is 4/50, which is 0.08. This is just an example of how you did estimates of this population parameter P. Okay, so if there's only one way to find an estimate for a given parameter, this will be a very short chapter. But in most cases, for most parameters, there are multiple reasonable estimators. So different people might have different opinion about how to estimate this parameter. People have different ways of like saying this should be a better estimate for the parameter. Oops, but yeah, you have to choose the right one for the for estimate your parameter. Because I'm not, I didn't cover like many different ways. I think for this chapter, I'm just going to talk about one most commonly used called maximum likelihood estimates. Or yeah, here I give you an example, like different ways of estimate something, but this is kind of not so important. This is just conceptually. What did I get? Okay. This is just conceptually telling you, okay, there are multiple ways of estimating a single parameter. Let's say mean. We can use the sample mean, the sample median, where we use this x tilde to denote the sample median. And we can also use something like this, the minimum plus the maximum divided by 2. Yeah, just different ways of to do the estimation. Yeah, I think because this population parameter mu is actually unknown, and we kind of do not know how good our estimate is without knowing the true population parameter. But what we could know is that which estimator would tend to produce estimate that closest to the true value. And we use so for different situations, and we're trying to get which estimator would tend to give us the best estimate, means is closest to the true value. Okay, and this is one way to quantify how close this estimator to the true population parameter, where we call it unbiased. Oops. Oh, is that because I see a chat? Okay. So we would call an estimator being unbiased estimator if its expectation, the expectation of this estimator equal to the true parameter. So this is important concept. What do we mean by unbiased? If we take the expectation of the estimator, we could get back to the true parameter value. Well, if theta hat is not unbiased, the difference between the expectation and the parameter is called the bias of this theta hat. So if we do this, we continue with the example of estimating P being P hat equal to x divided by n. And if we calculate the expectation of this P hat, so this is how I did the calculation, where you just take this 1 over n naught and times the expectation of x, where the expectation of x is from a binomial distribution because it's the number of sample successes. So this is from we learned that when binomial distribution is trying to describe the number of successes out of n trials. So the expectation of a binomial distribution is n times p, and this n canceled with this n. Now we get back over to the true parameter p. we can see that this p hat, x divided by n, is an unbiased estimator for p. Yeah, so this is the definition of bias, and what is the unbiased estimator? Okay. Oops, did I skip? No. Okay. Unbiased, now we want to know what is a good estimate for mean and variance. Say what is a good estimate, we could mean like unbiased estimate. Let's say what is the unbiased estimate for mean and variance? Actually, you can kind of guess because we have talked about, we use this x bar to estimate like our sample mean, to estimate the population mean mu. And we use this sample standard deviation to estimate the population standard deviation. Now I'm saying, okay, these two are the unbiased estimates for this two. Actually, this x tilde, if the distribution of your x is continuous and symmetric, you can also use the median as an estimate. It's also unbiased estimate of mu. So a parameter could have like multiple unbiased estimates. But here we're just talking about x bar and sigma hat square. Right, so sample mean and sample standard, sample variance. Yeah. Okay. For standard error. So what's the standard error? This is just kind of a vague definition for standard error, because whenever we have an estimate, we trying to get like the size of the error. We use the standard error to quantify that, which is just the square root of this kind of the variance is the standard, the square root of the variance, where it's our standard deviation. So people use the standard deviation and standard error sometimes interchangeably, but when you're trying to quantify like the uncertainty about an estimate, you normally call it the standard error. But this is how you get it, exactly how you get the standard deviations. We just take the square root of the variance of your estimates here. Yeah, so this is trying to capture the precision of the estimate, like how confident we are, like with this estimate. Okay, yeah, eventually we'll get to the methods of the estimation. I mentioned this, we would only talk about one in this chapter, and it's developed. So I said there are many different ways, and the most common one is developed by Fisher. And although Fisher is considered to be the single most important figure in 20th century statistics, he also developed the majority of his method in pursuit of his eugenic beliefs. This is just some kind of background information about Fisher. This person is really important for statistics, and you will see this more. You will see his name more if you do like more advanced statistical class. And his methodology is called maximum likelihood estimation. This is what we're going to talk about. for this method of estimation. So it's short, we use MLE to short for this maximum likelihood estimation. So where it's a method that finds the parameter that were the most likely to be the one that produce your sample of data. So maximum likelihood, just like what it sounds. We find the most likely one as your estimate. Okay. So once we got our estimator, I should say this MLE have many like nice properties. That's why we like it. So for large N, the MLE is unbiased and has the smallest possible standard error possible for estimator. So MLE is unbiased and have the smallest standard error. So the idea behind this MLE is that you think of the parameter as the function of the data. And we use calculus to maximize the probability. So once we get a function, I think I have an example here. Yeah, it's easier to go through example to see how do we use the calculus to get the maximize the probability and find the estimate of the parameter. So consider of flipping a coin 10 times, and X is the number of heads, and we can use binomial distribution for this X, right? N equal to 10, and this P, we will say we do not know this P. This is the parameter for this, for X, for the proportion for this random variable X. Suppose you get 3 heads, this is the data you observed. So you flip the coin already 10 times and you get 3. So this is your data, X equal to 3. And given this unknown probability P, and the probability of X equal to 3 is actually like this. If you just plug in the PDF PMF formula for binomial distribution, it's like this. And so this thing is a function of this unknown parameter P. So this is just a constant, and this P, this proportion is unknown. Now let's calculate this P hat, trying to get a P hat that can maximize this probability. So this is, we tried a couple of different values for P. This P is the one that we're trying to estimate. We tried a bunch of different values for P and calculate this value. And I think I ignored this constant part when I do the calculation here. But we compared like which p-value give us the largest this probability. So comparing this 3, so this one, when p equal to 0.3 gives us a relatively large probability to see the fact that we observed x equal to 3.
How do we know we start from that parameter? Like
0.2, 0.3. This is just an example that you can try many of different values. For this one, because it's a discrete distribution. Oh, well. Yeah, it doesn't matter if it's discrete or continuous. This is just an example showing you for different values of p, you get different probabilities. And we're just trying to find the p that maximize this probability.
So you're trying to get the one with the highest probability.
Yes, yes. So that's the idea of maximum likelihood. So when your probability is large, that's the most likely that you observed this x equal to 3. Yeah, so p hat equal to 3 is the estimate that maximizes the likelihood. Okay, so generally, we need to find the likelihood equation. So previously, we find this equation here, and we're trying to maximize this. And in general, when we do this MLE, we need to find the likelihood equation. And normally, taking the log of the likelihood, it will give you an easier formula to work with when you do the maximization of that likelihood equation. And once we take the log of the likelihood, and in order to find the maximum, we take the derivative of this log likelihood with respect to your unknown parameter, and then set this derivative to 0 and solve for this equation to get the value of theta hat. That's the value would maximize our likelihood. This is a bit, I think this is a bit beyond this course. Yeah, for this course. But this is just a general method when you do MLE. As long as you know what is MLE is doing conceptually, that's enough. And you will need this in probably more advanced statistical class. But for this one, I think for this chapter, we mostly just focus on like what is unbiased estimator and how do you estimate like mu and sigma square, those kind of things, and how do you estimate the p, like get p hat. Well, I think in future chapters we do not even talk about estimate this p. Well, yeah, this p hat is just this. We just use this x divided by n. Yeah, I think that's all we use in the future. And just conceptually, you know what is a bias for estimator, what is unbiased estimator. Yeah, not much information for this chapter. It's kind of all this 6 chapters we learned so far is more for preparation for chapter 7, chapter 8, chapter 9, where we just use some information from different chapters. We will need to do the inference, like hypothesis testing, intervals.
So this is just the groundwork for the stuff we're doing for the rest of the
Yeah,
class.
that's why you see, oh, there are so many concepts. Yeah. And I have like I said, we will have our first exam after next week. So the week following next week. But up to today, it's all the information will be covered for exam 1. So you have a whole week, more than a whole week to start review.
It's from chapter 1 to 6.
Yeah, chapter 1 to 6. Chapter 6.
So for the homework for chapter, you're gonna assign 1 for 5 and 1 for 6.
Yeah, I think I'm thinking to combine them because the due date would be yeah, I think it's better just put them together. Yeah, or yeah, I'll see. It will be the same amount of questions. Either I put the same deadline for 2 homework. The exam is testing for what? Okay, the exam is more like web assigned questions. oh, I have this topic list here. And yeah, it's through WebAssign. It's I will have more information provided for you. Yeah, I have put this topic list here just for you to go over the material and what will be tested, and make sure you know how to solve problems on your homework. Yeah, it will be really useful to go through your homework, and also like go through your notes. Make sure you know where to find what concepts. Yeah, oh, no problem. And yeah, I'll post this on Blackboard.
Do you know about how many questions you're thinking? the test will be?
For the test, there are, yeah, I have some questions selected for the exam, but not all of them. So for the exam, all like small questions would have the same value of points. It's not like the whole like multi-part question have definitely more points than like just single question, single question. How many?
So this,
I think it's like, yeah, but it's hard to say for now.
oh, no, I was just wondering if you
So
had
this
an
will be
idea.
October 6th.
Yeah, October 6th, the same time for our class. It's during our class time through WebAssign. Yes, you can use RStudio. That's why I gave you the exam on WebAssign, so you will do it. You will definitely need to use R, because it's just like your homework. Lockdown browser active. Yeah, no internet, no, like no Google search.
But do we have to record ourselves like testing?
I don't think so.
But
I
it's just through
will-
WebAssign, right? that you-
Yeah, through
Okay.
WebAssign. But I heard from other professor that it's, well, they said there is a way to kind of monitor if you go out of WebAssign or go to your internet, but I would have to ask them again to, this is my first time like doing a test online. And this is kind of special because you have to use your computer.
Right, that's why it's a little bit difficult, because using lockdown browser, it won't necessarily let us use R.
Oh,
Oh, yeah, really?
Yeah, because it basically like shuts down your computer except for this one.
one
Screen.
interface.
Yeah.
Oh, yeah. Well, I don't know. It's, yeah, I would have to ask other professor like how is this done?
Programming assignment to do. Like,
And then
no, he's giving us like.
So this will be on Blackboard, and start review early. Don't wait until
Yes.
the last minute. Okay, I think that's it for today. If you have questions, oh, by the way, we have our TA. Like if you have any problem on like homework questions, you have like a whole week to like start reviewing. And if you have question about the homework, why I got this wrong, make sure you do it again and know how to get it right. Yeah, that's it for today.
Thank you.
No problem.
He's doing, basically, like the quizzes, or then maybe like writing